this was an example of an integer linear programming problem that we said has some features that actually enable a more efficient solution. What we will look at now is how do you solve with efficiency, essentially the proof that there is an efficient solution. That proof need not be the way you would actually solve it. This formulation is enough, and if you submit this set of inequalities to a standard solver, it will find an efficient solution to this. How it solves it we will not get into, but let us look at a conceptual proof that this is not a difficult problem, not like the general integer linear programming. Okay, so, what characterizes this is that you have these coefficients. In each of those inequalities you have exactly two variables, and those coefficients are 1 and minus 1. That is the special case for which an efficient solution is known. Other special cases are also there for which it is known, but this particular special case has an efficient solution. So, let us go through a set of arguments to ultimately prove that this particular problem is not difficult, and in the process we identify what is the solution to this sort of inequalities. Okay. So, what are the possibilities anyway for this set of inequalities? It is possible for you to set up these inequalities such that there is no solution. That should be easy. You can set up some pairs that are inconsistent with each other and you end up with no solution. It could also be that the system has an infinite number of solutions. That can you see that if you have one solution, then you can generate any number of solutions from there. Since all are of the kind x minus y is equal to constant, if you increase all the r's by some fixed constant, both r1 and r2, r3, all of these are increased by the same constant, then they would respect the same constraint. As long as there is one solution, you can generate an infinite number of solutions. As a special case, you can actually set an arbitrary Ri to 0. Why not? We said that I can add or subtract anything, any constant. Specifically, I can subtract whatever is the value of R1 from all the other R's, and I would get a valid solution. Okay. Let us go through a set of arguments with a new graph, yet another graph that is constructed specifically for this proof. Okay, so this is just a set of conceptual arguments like we said. So, I have this set of constraints. Of course, each of those constraints is of the kind R a minus R b less than or equal to k, where k is a constant. Okay. So, you build a graph in which there is a node for every R I value. Okay. And corresponding to every single inequality there, you introduce an edge in that graph in the following way. If that constraint is R a minus R b is less than or equal to k, then you have an edge from node B to node A with the weight being k. Why is it this way is not obvious, but this is just a construction for us to prove something later on. Okay. So, if I have R1 minus R2 is less than or equal to 1, I have an edge from N2 to N1 with the weight being 1. Okay. If it is a negative number, then the corresponding weight here is a negative number. The construction is clear. So, this is first. Second, you add an auxiliary node to the graph T, and from there you introduce 0 weight edges to all the other nodes. Why we will just see, but this is a construction. It turns out that it does not violate some property that we will use later on, but it enables us to find the solution. So, that is what we have done. We constructed the graph and you added one more node T from where you just introduced edges to all the other nodes. Weights are there on all the edges. So, on these new edges I just put a weight 0. Okay. Now, you find the shortest path in the graph from node T to all the other nodes in the graph. Okay. Let us look at some examples. From T to node N2, what is the shortest path? Remember, shortest path can be negative, right. So, actually that shortest path is minus 2. Where does it come from? That is the path, right, 0 and minus 2. So, you add up all the edge weights along the path, that is the cost of the path, that is the path length. Similarly to N1, the shortest path is minus 2. Why is that? Right. So, that is the path. So, you find the shortest path from T to all the other nodes. Okay. The assertion is that this shortest path length actually gives the desired Ri values for all the nodes in the graph. Shortest path length from T to all the nodes in the graph gives us the desired Ri values that respect the constraints that we had set up. Okay. Why it should do that? Let us argue in the following way. Consider that there is some shortest path we have found from T to node A, and I have separately found a shortest path from T to node B. Okay. And that length is given by the SP of that path from T to node A, whatever the path is. Right. Shortest path by definition must mean that this path length must be less than or equal to this path length, because that is also an alternative path to node A. So, if that other path was shorter, then that would be the shortest path. So, that is the assertion here. It could be equal also, because in fact that path here could be the shortest path, right, path through NB, that might be the shortest path, in which case it will be equal perhaps, but otherwise that other path must be shorter than this one that includes this edge from NB to NA. So, this must be true, right, this is just the definition of the shortest path, otherwise it would not be the shortest, which means if I just take this to the left, I have the shortest path T to NA minus the shortest path T to NB is less than or equal to the weight of that edge. Okay, that is just rearranging, taking that term to the left. Okay. Now, if I say R A is the shortest path from T to NA, R B is the shortest path from T to NB, what was this weight anyway? This weight was the k that came from the constraint, right. So, if I have found the right shortest path from T to all the nodes, this is some arbitrary node NA and NB. If I have found the shortest path, and since this is respected by the shortest path, I would have R A minus R B. If I just choose R A to be the shortest path to A and R B to be the shortest path from T to B, then I would have R A minus R B is less than or equal to this, which is just a rewriting of this equation. But this is nothing but k. The shortest path argument just enables us to argue that R A minus R B, that particular inequality is satisfied. I have an edge here for every constraint that I had, every inequality that we had set up, right. There is a corresponding k, there is a corresponding, each of those inequalities results in one edge being added to the graph, and therefore, this argument just tells us that if you just choose the R A and R B to be just the shortest path in this augmented graph, then you have a set of values for the Ri's that respect all the constraints.
So how will this graph portray the no solution scenario?
I will come to that. But if there is a solution, this actually gives us the set of solutions. In fact, it gives us all the RIs, because it is essentially the shortest path from T to all the nodes, right. So, we would have an R vector, retiming vector for all the nodes that is valid once we are able to find the shortest path like this. Any questions about this argument? This is fairly simple actually. There are situations when the set of inequalities does not lead to a feasible solution. In fact, this shortest path algorithm also sometimes does not return a feasible solution. In fact, we will show that these two are actually the same situation. Shortest path does not work. When will it not work?
Sir, R1 is if it is positive number.
If what is a positive number?
I mean, we are calculating the shortest path from T to any node.
Right.
And if, like for say in this case, if that -1 as from n3 to n1 was not there,
okay.
If we say it was +1, then the shortest path, our algorithm would return a 0.
Yeah, which is okay or not okay? Is the retiming value of 0 okay for some nodes? It's fine, why not?
So the
That
example you have shown here is the issue.
Yeah, there are some times when the shortest path does not. If you allow negative edges, then what might happen is that you may have a cycle in which the path length is negative. It's possible, right? What happens if you have a cycle with a negative sum of path lengths and you are trying to find the shortest path?
Keep on going.
Yeah, if the shortest path is you arrive at one of those nodes, you can keep going around that cycle and the path length can keep reducing. So, that the shortest path is not properly defined there. The algorithm that people use for finding the shortest path, single source, multiple all destinations shortest path, is what is called a Bellman-Ford algorithm. This is a variation. There is a Dijkstra's algorithm that finds the shortest path between a pair of nodes, but this Bellman-Ford is a way of efficiently finding the shortest path from one source to all the destinations. This is what you would use for this problem, because we need the shortest path to everything. But that algorithm will return an error if such situations are there in which you have a negative cycle. Okay. So, essentially shortest path is not defined. The algorithm might not actually return a valid solution, but what we will argue, this is exactly the infeasibility case of the set of inequalities in the following way. If there is a negative cycle, what does it mean as far as the set of inequalities is concerned? This is our set of equations. Okay. So, negative cycle means you start from R1 to R2, R2 to R3, R3 to R4 and so on, Rk minus 1 to Rk, finally Rk to R1, that establishes the cycle. And let us say we found a cycle with a negative sum of edge weights. What does it become? So, if you just add all the left hand sides and the right hand sides in this set of inequalities, you have 0 on the left hand side, because every Ri is appearing once with a positive coefficient +1 and once with a -1. So, this is 0. Sum of all of these, in fact, we are saying is negative, right. If there is a negative cycle leading from this set of equations, then you actually have a negative value here. So, essentially what you are having is, if you add up everything, you have 0 less than or equal to a negative number. That is not possible, right. So, essentially that Bellman-Ford algorithm can be used directly for our problem. If it fails, it means that there was no solution anyway to the set of inequalities. So, you just run the single source shortest path algorithm to that augmented graph, and what we have as output is the set of retiming values for all the nodes. So, that solves the retiming problem completely, or there is something else still to take care of. You got the Ri values, what else is there? array values tell us number of registers that should be moved from the output of every gate towards the inputs. Is there something else to do or problem solved? Let us see what is the overall retiming strategy. I compute those D and W matrices. This is a 2-dimensional matrix, right, to both D, and because from every node to every other node if there is a path. So, I to j, Dij captures that, Wij similarly is the path weight. Right. So, you compute those matrices. For that phi, you set up the inequalities of this nature. So, this set of inequalities always shows up. Remember, this arises from the need to have the number of flip flops on the resulting circuit after retiming being greater than or equal to 0. This one is a conditional inequality, sometimes you have it, sometimes you do not. If it turns out that that Dij is greater than phi, then you would have it. So, anyway, between these two you have a bunch of inequalities which you would then solve, let us say, with that strategy that we just indicated. By the way, that proof that we went through of augmenting that graph with a new node and then running shortest path, you do not necessarily solve it in that way. We just use that argument just because the shortest path computation is a known algorithm. You might not actually use shortest path to solve it. There are other ways to solve it, but this argument was essentially a polynomial time optimal solution to the retiming problem. So, you can see that if I just apply that, I have an optimal set of solutions. Of course, I may have an infinite number of solutions, but I have one set of solutions that is optimal, as long as optimality is defined in terms of finding a retiming vector that satisfies the clock period. There is one thing that is still not addressed. We can find all the Rij values. So, we first determine the set of inequalities. After determining the set of inequalities, we can go ahead and solve it using whatever mechanism, but efficient solutions are there, optimal efficient solutions are there. The question though is, who gave the phi input? This is an input to this whole algorithm. In fact, the set of inequalities are actually determined by that condition, and that condition involves phi. So, it is pretty much an input. So, if our problem statement was given a clock period, find a retiming vector if it exists, then it is enough what we have. But that might not be the problem statement. Problem statement might be, given the circuit, find the best clock period. Right? What is the best clock period for which you can find some retiming vector that satisfies that timing, right. So, if that is the case, then I still have to worry about how to generate the phi, because this I started off with some phi, right, but I do not know, maybe a better phi is there, right. I found a solution, given a phi we outlined a mechanism for finding the solution, but that still does not tell us how to find the clock period itself. Right. It must be that if you keep reducing the clock period, after some time you will not find a feasible, if you make it too small, then you will not find any feasible solution. Okay. So, that outer loop is still there in the retiming, which is I have to find a way of reducing the clock period that is the input to this strategy until there is no more solution. So, what strategy can we take? You can take a simple strategy that just decrements by some fixed constant, right, by some small constant. You do have to be careful about the number of times you iterate through this solution, because you do not want to run it too many times. Even though it is efficient, phi can be a real number, right. It is not, phi is not an integer, not necessarily an integer. So, we can do a little bit about it, which is how to minimize the number of times I set up the equations and solve the equation. Solving it is efficient, that we have a good algorithm for, but there is this question of how many times I will solve it.
So, we can reduce the time by a large number, so that in the first iteration we get a no solution, and then we can apply some binary search kind of strategy, keep halving the time.
Right.
So, that case the number of iterations that are.
Let us say I first try with a large phi equal to 10 some such, and for that I am able to find a solution. A binary search kind of a strategy suggests itself as an obvious mechanism for solving this. If 10 works, then I can try to make it 5, right. So, if 5 also works, then I can try to make it 2.5 and so on. When do I stop?
So there has to be two constraints. One is number of iterations, and the other is there can be another. What?
Looking at the netlist, there ought to be a minimum that you can easily figure out. What would that minimum be?
Setup plus hold plus combinational
Delay,
that we require.
total delay,
The breaking set.
Certainly, each of those gates has a combinational delay. The clock period can't be less than that, right. Whatever is the max of all those combinational delays of the gates, the clock period had better be more than that, because that gate, of course, you need enough time for that combinational circuit to work. We are not doing the retiming in a way that we are moving them into the blocks, into the gate. We do not do that, right. So, that certainly gives bounds, imposes a lower bound on this, but as it turns out, you could actually be more efficient than that. This argument can be extended from the gate lengths to actually the path lengths. The path lengths we actually computed already, those Dij values are the path lengths. What do we need at the end? Whatever the solution is, we can argue that the phi can be equal to, at least the simplified way in which this problem is formulated, it has to be one of those path length values.
The best value. Critical. That's the best value.
So, it is like this, I went through the Dij matrix and these are my different path lengths, they are distributed all over. We can argue that the clock period that we choose must be one of these values, because if it was not, say I found a solution for phi equals 14, I just tried 14 and it turns out that I managed to find a solution. If I can find a solution for phi equals 14, I must be able to find a solution for phi equals 13 also, because there is no path length between 14 and 13, right. Any path that you combinational path that you look up, well, these are the critical combinational paths, right, the Dij. If there is no Dij between 14 and 13 and 14 is passing, then it must be that the critical value is this. Between 14 and 13 I need not search, because there is no path that is actually adding up to that much. So, if I just list all the values here, then in fact I can still do binary search, but only among these values of Dij. The point is there is a binary search, but that binary search is not over the real domain that was causing confusion, right. I do not know when to actually stop, when to start and so on, but it could be that I just take this set of these delay values and the binary search is just there. So, a relatively small number of iterations should be enough for us to converge into the appropriate phi. Of course, other hints might be there from the circumstances of the design.
So basically you are saying take them in tuples of like 20, 16, 16, 15, 15, 13 and then try to get.
No, it's a, this is an array, right. You store this in an array, you start with 13. If 13 fails, then you go here. If 16 fails, 16 passes, 13 fails, then you go here. The standard way you do binary search on an array.
But you would want to go between 15, 13 also, right?
Why? We just argued that you should not, that our solutions are exactly at these points. You do not want to explore the space between 15 and 13.
That's not very.
What I am saying is, if there were a solution where I had phi equals 14.9 right. I tried 14.9 and I found a solution, but in fact there is no path length there that is adding up to 14.9. It must be that I would succeed even at 13, because remember there is a path length of 15. So, if 14.9 I am able to find a solution, it means that I am able to find a solution that is less than 15, that 15 is not what is determining my clock period. The next path delay that determines the clock period is 13. Therefore, the range in between need not be searched. It is like if you had nodes with delays 3, 4 and 2, what are the possible clock periods at which this circuit can be run? One is I can say phi equals 3 plus 4 plus 2, 9, that is the solution. Other is it could be phi equals 7 from 3 plus 4. Could also be phi equals 6 from 4 plus 2, or phi could also be 3, phi can be 4, phi can be. These are my only path lengths. What we are arguing is that I cannot have an optimal solution of phi equals 8 for this circuit.
It will not be the corner case.
If I can find 8, it must be that I can lower it to 7 and it would still be okay. Right. Why? Because let us say that was the solution, putting a resistor here was the solution for phi equal to 8. The path lengths are such that you could reduce it to phi equals 7 and it is still fine. Point is, there is no need to test the numbers in the interval between two successive path lengths. Remember, this is a little bit of an idealized argument. There are other numbers that we need to take care of. There is propagation delay of the flip flops, the setup time of the flip flops. Those are okay, those do need to be handled, but the way you can handle them is that you leave a certain margin for them, and this analysis is in term by excluding those margins, and finally you can add up the setup time and so on to the path delays. Okay, that completes the retiming problem. This is an instance of a synthesis problem for which an optimal solution is there and can be efficiently found. This also is pretty deterministic and pretty straightforward, right. The outer loops, of course, the inner solution mechanism itself is a polynomial solution that gives the optimal answer, but the number of iterations is also small. And unlike some of the other problems where we said we will just use a heuristic because it is a difficult problem, this problem is not difficult. There are other issues which are common issues to all of synthesis, those still show up here, which are of the kind that those delays are really estimates of delays, rise times are different, fall times are different, geometry is not taken care of. All of those which are common to many other steps of synthesis, those of course are still there, but this particular problem, the way it is formulated, it is a simplified version of a problem, but this problem in fact has an elegant and attractive solution. With that, let us move on to the next topic, a little lower in abstraction detail, that is logic synthesis. This is a topic that we have some understanding of. Right. Logic minimization is something that we have been exposed to in various ways earlier. How to do it efficiently we may not have studied, but certainly how to do it, how to represent this, and at least a visual solution involving the K map you might have already seen, that I am essentially representing a truth table of all the values of the inputs and trying to come up with a solution that minimizes the number of literals or indirectly reduces area, optimizes for area by minimizing the number of literals in a Boolean algebraic expression. So, we start off from there. We will first look at some ways of representing our designs. Then we will look at essentially two phases. The logic synthesis can be thought of as consisting of initially a logic optimization phase that is technology independent. Technology independent means that it does not matter what particular ASIC library or FPGA or whatever the target architecture is, we can do some logic optimization anyway. That is at a little abstract level. The sort of K-map optimization that we have seen belongs to this level. Right? We do not really care how you will finally implement it, but we go through that K-map optimization in a way that you just try to minimize the number of literals, hoping that it translates to a minimized circuit no matter what gates you use, assuming of course that they are reasonable standard cell that have already been designed. Still, the strategy would be different based on whether you are targeting a two-level architecture or a multi-level architecture that we had already seen in the context of the FSM and coding, right. So, it is the same thing. So, that much you do need to know, but within that if you know two level, then there is a certain kind of optimization. If you know it is multi-level, it would be a different kind of optimization. That is one. The second step would be a technology mapping or a cell library binding, both are kind of equivalent to each other. This would take us from an optimized result from the first phase into something that is now generating an optimized netlist for the particular target architecture that we have in mind. Here it may be a particular ASIC library or a specific FPGA, because those numbers that we use are specific to a particular library, right, area numbers, delay numbers and so on. If you change the library, then all of those numbers will change, and therefore, the selected netlist might be different, optimized netlist might be different. In the first phase, we do not worry about all that. This is again in the interest of simplification of the passes. We just try to minimize the number of literals, for example, in an area optimization, without necessarily taking into account the area of the NAND gate, area of the inverter and so on. The overall synthesis step is divided into these two phases, the first of which is a little abstract. Of course, logic synthesis itself is more detailed compared to the other synthesis steps that we have seen, but within that too you can think of a little higher level of abstraction and a lower level. So, the lower level would be taking data from the library elements and optimizing in those terms. Okay. Before we can get along with synthesis, let us just do a quick recap of Boolean algebra in case you have forgotten some of it. This B being a set of 0, 1 refers to what? The rest of the algebra is built in terms of variables that take values only 0 and 1. Right. Operations are defined, and or and so on. There are these properties of each of those operations. Commutative means that A dot B equals B dot A plus B is B plus A. There are rules for distribution, there are rules for complement. There are a number of other properties that should just be a quick recap. Associativity means it does not matter whether you pick up B plus C first or A plus B first when you have such a sequence of operations. Absorption, these rules ought to be familiar. De Morgan's laws ought to be familiar. So, this is all familiar space. Let us introduce some conceptual representations to enable us to argue about specific synthesis optimizations later on. Let us define a 3D Boolean space, the 3 arising from just us having a function of 3 variables. Okay. So, assume I have A, B, C as my 3 variables, then you can imagine a cube in which every vertex or every corner corresponds to one min term. If I can label it with zeros and ones. So, one of this is 0 0 0, that is 1 1 1, this is 0 1 1 and so on. There are 8 vertices in this 3 dimensional cube, and in some straightforward way you can map a min term onto each one of those vertices. 0 0 0 means that all the ABC are there in complemented form, all ones means that I have ABC uncomplemented, and in some node like 0 1 1 means that it corresponds to A prime B C. So, the position here refers to the variable there A, B or C. You can see how to generalize that. If there were n variables, then you would have an n dimensional space. Then the Boolean function in general is a mapping from a vector of size n to a vector of size m. So, the function has n inputs and m outputs. That is what that function is doing. Here we can also introduce don't cares. Incompletely specified function means that that don't care could be there on the output. It is not just a Boolean which is just 0 and 1, but every one of those m values on the output could also be don't care. How about on the input? Should I extend this to also have don't care on the input? Do I have any more information? For example, in this case where I have a don't care on the output, also a don't care is there on the output, is that giving us any more information than if I were to have only Boolean values on the output?
Yes, we can reduce the literals, common cubes.
Yeah, it is giving us something more. By saying that I don't care about a particular output value for an input combination, I am giving some flexibility to the tool and say 0 is okay, 1 is also okay. That is different from me insisting that I must put a 0 or a 1 there, right. So, in some ways it is actually more information, it is a different function. But on the input side, so the input vector, if it was like that, let us say I have an output vector like that. Instead, if I said 1 1 this, the output is 0 1, am I giving any more information? This was a truth table, right. Function means that for every input combination I should specify the output combination, that is a truth table, right. In a truth table, if a 0 here is replaced by don't care, it means something, technically it could be a different function. On the input side, if I replace a 1 or a 0 by a don't care, what am I essentially doing?
I am saying that the output function is now dependent only on 2 variables instead of 3.
Well, the equivalent way of looking at it is, this is nothing but I am saying 1 1 1 0 1 and 1 1 0 0 1. This is a convenience for me by just saying this is don't care. I am essentially referring to 2 rows in the truth table, but I have not given you any more information. These two are the same, right. So, this is a way of compacting the truth table, compacting the input, but I am really not telling much more about function itself. On the other hand, putting the don't care on the output, I am saying something about the function. So, that is why I have still B on the domain side, it is the code domain where it is essential that I should put a don't care. Let us define a few other things. We are talking about these vertices on that n dimensional space, right. I am using 3 dimensional examples all through. This discussion is more or less synchronized with the logic synthesis discussion in the textbook, right, and this representation is also from there. Okay. Let me define 3 sets, an on set, an off set and a don't care set. So, on set is the subset of the domain for which the function value is 1. Okay. So, those are all of these points. I have 3 of these rows having a 1 at y. So, 0 0 0, 0 0 1 and 0 1 1, that is these 3 points are in the on set of the function. Similarly, offset consists of 3 points. Okay, so that is off, and I have these 2 points in the do not care set. Every point in that space, every vertex in that space belongs to one of these sets. I may have multiple outputs, right. A function may have more than one output. If yes, then I just have a different cube. It is an n dimensional cube in general, remember. I have a different cube for each output. For x I have a cube, and for y I have a different cube. Okay. So, keep that in mind, that is all that is there. We will use that in various ways later on. Let us introduce the idea of a cofactor. So, given a function of n variables x1 to xn, the cofactor of f with respect to a variable xi is obtained by just substituting xi equals 1 in that function. And the cofactor with respect to xi prime is obtained by just substituting 0 wherever xi occurs in that function. Okay. So, example is if this was my original function, then cofactor of f with respect to a is if you substitute a equals 1, right. So, if a equals 1 means you get b from here and this becomes 0. So, you have b. F a prime is if you substitute 0 here, which will pick up b prime. Those are my cofactors. This is just a simple definition. Let us look at one standard result called Shannon's expansion. Any Boolean function of n variables can be expressed like this: xi, you take any one of those variables, xi times cofactor of f with respect to xi plus xi prime times the cofactor of f with respect to xi prime. Okay. In that example that we just saw, this was the function. We determined the cofactors with respect to a and a prime. If you just substitute a f a plus a prime f a prime, you would get essentially this is multiplied by a, that is multiplied by a prime, you get back the original function itself. Why this is true in general, it is not hard to see. We can informally derive it in the following way. Suppose you have some function of a large number of variables, okay, and I would like to pick up one of them. Let us say these cofactors with respect to a I am trying to pick up. Then this expression is colored in the following way: the yellow terms are those that have an a in them, the blue terms are those that have an a prime in them, and the rest of the pink terms have neither a nor a prime. Okay. So, if I group them, I have a times all of these plus a prime times all of these arising out of the yellow and the blue terms, and these that have neither an a nor an a prime, let me put them into those expressions in the following way: let me multiply them by a plus a prime. Nothing changes because that is 1. So, then if I regroup the terms, I essentially am multiplying a by all the yellow terms plus all the pink terms, right. And similarly, a prime is also multiplied by the blue terms and all the pink. The pink terms go in both the places. But what is this expression anyway? This is nothing but the cofactor of that original expression with respect to a. You drop all the a prime terms, right, and you drop a's from the ones that have a, that is the yellow terms, and the pink terms, since they have neither a nor a prime, they would show up in both the cofactors, right. So, that is what I have here. Similarly, this is the cofactor of f with respect to A prime, and so that is what I have. So, that is my result. You can see this is an informal, but you can easily generalize this into a formal proof if you wanted to. This is a result that is used at various places in logic synthesis. So, it is a sort of a very fundamental result. Okay. Let us quickly move on to representation of the Boolean functions. Starting off with the tabular forms, because those are the ones that are familiar. Truth table is essentially a two-dimensional table in which there is an input part and an output part. We have already seen this is just a recap. What characterizes the truth table is that it is a complete listing of all the points or the vertices of the input space. Every row corresponds to one of those vertices in the cube, and if you have an n input and m output combinational function, how many rows are there in the truth table? Exponential in n, right. The number of inputs is what it is exponential in terms of, right. Does not matter how many outputs are there. So, all the row vectors that you could compose of zeros and ones of length n is what shows up there, each becomes a separate row. And output part, we will say it can have 0, it can have 1, it can also have do not care. So, it is a vector of size m. So, this of course is a nice way to visualize small functions. Problem of course is that explicitly doing it and manipulating the truth table becomes inconvenient when the number of variables becomes large, but still that is the first thing that you can start off with. You can generalize it in the following way. Still a tabular form, the multiple output implicant is a sort of a compacted version of the truth table itself. This is also two dimensional table, there is an input part and an output part, but the input part you are allowed to have a do not care, which could be used to drop some of the terms if you can properly find those combinations. You look at two rows, and if the results are the same, then you could combine them with the do not cares in some way. Okay. Output is still the same, but being an implicant here means that if there are rows for which all the outputs are 0, then we drop it. We will define formally implicant later on, but a cube is an implicant if it leads to an output of 1 for at least one of the outputs. So, if all of them are 0, then we drop them. That is a way of reducing the size of that table. This size is not necessarily exponential. In the worst case, it is exponential. In fact, you have functions that have an exponentially large number of implicants. There is nothing you can do about it, but often it could be that this could be used to compact the specification. So, those are just the two tabular forms that we will look at. One is truth table, you have one min term per row and all the input combinations, but in that multiple output implicant table, you have one input cube per row. That is not necessarily a min term per row, because many min terms can be combined into a single cube. You retain those cubes that are implicants, means that you drop this cube and you drop this cube, because the output is 0 0, all the outputs are 0, then you drop it from the table. Then you can see whether there are rows that actually lead to the same outputs. Okay, so, you have two rows with outputs being same, and I have 0 1 0 and 0 0 1, that could be compacted into one row in that table. Same thing here. So, that is a way of a tabular representation that sometimes at least can avoid the blowing up of the number of rows, the number of entries, or essentially the size of the data structure that you are using to capture the function. So, those are the tabular forms. Let us move on to other representations. Expression forms are ones that are common, of course. You can have Boolean functions represented as expression of literals that are combined by some operators or an AND. It could be a single level expression, which means that there is only one operator. So, literal can be a Boolean variable or its complement. Okay, both are single. Literal single level means that you have only one operator that is operating on possibly several literals. So, that is one example, this is one example, but this is too simple, it cannot represent all Boolean functions. We certainly need to be able to represent all the Boolean functions. Two level is of course something that we should know. It could be a sum of products, it could be a product of sums. This is good enough for us to represent all Boolean functions, of course. Sum of min terms or equivalently product of max terms are what are called canonical representations. Canonical representations means that given a function there is only one way to represent that. Sum of min terms, you can see a given Boolean function can be represented using many different expressions, but in terms of min terms it is still the same, right. So, your expression could be a prime plus b c, right. This is a more compacted form. That expression could be written in other ways also. For example, this can be a prime plus b c can be expanded as a b c plus a prime b c, right. So, and similarly this can be expanded. So, there would be many different ways of writing that same function, but what we are saying is that if I reduce it to only a sum of min terms form, which is all the variables are there either complemented form or in the non complemented form and so on, then there is only one way to represent every function. That is obvious, right, because that essentially corresponds to taking the set of on points in my truth table or in my 3D space or in my n dimensional space. It is just a set. Of course, the order in which you write these could be different, but this is essentially a set of min terms that we have taken. A set does not have ordering. So, there is only one way to represent this. Max term is the equivalent thing if you do not use sum of product, but you use product of sums. So, both of these are canonical, all the other forms are not necessarily canonical. That multiple output implicant table, that is not necessarily canonical. Truth table is canonical of course, but the other one that we showed, this one is not necessarily canonical. You could actually have different tables that are derived from the same truth table. Expression form could also be multi-level. Multi-level essentially means that you have an arbitrary nesting of Boolean operators. You can have plus operator, you have AND operator to the result of the plus, you have invert operated operating on the result of a plus, and you have this being a different function, you have combined in different. So, any level of hierarchy could be there. Could also have a factored form that is somewhere in between, where what is allowed is here. So, you can have a literal, that literal is a variable or its complement. You can have a sum of factored forms, you can have a product of factored forms. This is a grammatical specification. F equals F plus F means a new factored form is generated from two other factored forms by applying the plus operator. It could be a product. This is a constrained form of that general multi-level representation. In what way? If this were the only way for me to generate expressions, how is it a constrained form? What is it that you can do here that you can't do here? You can have complements, you can have sum of things, you can have product of things, which allows hierarchical composition or not of any depth of that expression.
We cannot have both of them simultaneously.
Multi-level we can't have.
Yeah, we were just trying to see what is the difference. How is this more constrained? Multi-level is the most general form. So how is this different? If I say that you are allowed a literal is a factored form, sum of factored forms is a factored form, product of factored forms is also a factored form. What have I left out?
Sum of products of a factor.
No, product of two factored forms is also a factored forms. Okay, so that is also a factored form. Plus of two factored forms is also a factored form. So this is fine.
F into F dash.
Yeah, see, f prime is not there, which means a plus b prime is not a factored form. Literal can be complemented, but an expression cannot be, more complex expression cannot be complemented. So anyway, that is one way. It is a simplified version of the multi-level logic. This is also complete in the form of you can express any Boolean function in factored form, simply because sum of products is fine. So sum of min terms is fine, and that is good enough for us to capture anything. These are all trivial data structures that we have seen so far. The binary decision diagram is one on which we can spend some time. This is a data structure that was designed to capture Boolean functions in a somewhat non-trivial way. Let us define the structure itself, and there are some very interesting properties that we can study of these BDDs, binary decision diagrams. This diagram consists of a set of decisions, the value being true or false, the value of an expression or value of a variable being true or false essentially is what we mean by that decision. This is such a structure. Each of the nodes corresponds to an evaluation of something. What that thing is we have to say, but we will label it with that expression. An expression is evaluated, and if we are at a node, we evaluate that expression. If it is true, then we go one level down and evaluate whatever is the expression at that node. If the result were false, then we go down and whatever is the expression there we evaluate. So there is a series of decisions that we take. At each step we do an evaluation, and based on it is true or false, we go down one path or the other of this diagram. Ultimately we end up with a leaf level which is essentially true or false. So that is all that is there. If that path is false, then the value of that function that is captured by that data structure is false for those expressions that we evaluated along the way. So you can see that if I attach a variable name there, what I am saying is if I follow that path down, right, if a were 0 and b were 1 and c were 1, then the value of that function is 1. That is what we are trying to capture. But in general a decision diagram leaves this unspecified, though. You can have a there, you can also have a more complex expression there. We will constrain the definition for it to be more meaningful, but a decision diagram in general could be anything. Binary just means that there are two results, 0 and 1, but you could have more complex expressions there, and that is also fine. We will try to avoid that. We will try to come up with a subset that is more meaningful, but this is what is a binary decision diagram. At the end of sequence of decisions, you have the result true or false, and that true or false means that the function value is true or false for that path that you took. This is represented by a tree or a DAG kind of a structure.
So we cannot have any operator kind of link between the
You
literals
don't need
in this.
Everything has to be implicitly captured by these decisions, but we will see later that if I have an operation, what does that become in this tree. But this is an expression essentially. Of course, the data structure is meaningful if any Boolean function I am able to represent in this data structure, right.
This is for one output. So if I have multi-valued output, then I will have different trees for each of the output.
Yeah, we will get there, but this is just
All the
a
paths
single.
will become a sum to give the output. in this. So, if I have,
we may be jumping ahead, but what we would actually do is we build one structure, but each node would correspond to some function. Right. So, if I had more than one output, I would still build one structure, but the root would have something, some other node would have something. So, I will try to capture all of them in one structure. Why one structure? Because we may want to reuse some of the decisions, but we will get there. So, it is represented as a tree. As you can see, this is the root of that tree. Well, whether it is a tree or a DAG, essentially there is a direction that is implied in the structure, which is you traverse this structure from top to bottom. DAG or a tree, it is just that you start from the top, but let us say if you have a structure like this, and it turns out that these are actually identical. So, this decision diagram in some obvious ways can be thought of as a tree. You start from the top, two directions, then you get to the next one, two directions. So, it is a tree kind of a structure in general, but you can end up with some of these subtrees that are actually identical to each other. Then you could argue why have two different, instead the structure should be such that you have only one tree. This is just the reason why it is not in general a tree structure, but a DAG structure. It is because there are common subtrees that you might want to exploit. Right. Equivalent tree is of course also there, but if they are there in order to minimize the size of that data structure, we would possibly end up with a DAG structure. In this tree, what we are formally doing is the nodes represent decisions, that is fine, but for us it could be a single variable or a complex function. Again, we are just talking about a general binary decision diagram. There are some other decisions that we can make. First, let us define an ordering of the binary decision diagrams. What we are doing is, you have your variables a, b, c, suppose it is a function of 3 variables that we want to design, then you associate an ordering with these decision variables. So, these decision variables in this BDD are nothing but our Boolean inputs to the function, and you impose an ordering where you say A corresponds to index 1, B corresponds to index 2, and C corresponds to index 3. That is where the ordering comes from in the name. So, we are moving in the direction of making that structure canonical. That is why these limitations are being imposed. But one thing is, let us get out of this mode of any expressions, and instead each of these nodes is associated with a variable. Okay, one of the input variables, in this case it can be A or B or C. These OBDDs can be made canonical, which means that if you have one function, you have exactly one representation. We need to do something more to that, but the ordering is essential. If for that same function you change the ordering, then you would have a different BDD structure. So, an ordering is defined. In this representation, there is an implicit ordering, that it is defined in terms of an ordering. Why do this? Efficient algorithms can operate on the ordered BDDs. So, we are moving in the direction of minimizing the size of the data structure, but also improving the efficiency of whatever manipulation we want to do later on with that data structure. So, those algorithms can be polynomial in terms of the number of nodes. So, it is good to have a smaller number of nodes for that structure, but of course, some functions may be such that your number of nodes may be exponential anyway. It is just the general case that a typical function may be compact in terms of its BDD representation. OBDD means you have an index that is associated with the variables. You do not necessarily need a node at every stage. After B, if B were 1, then you moved in one direction, you moved to a different node. If B were 0, you were directly saying that the output is 0. We did not go through another level of nodes there, but that is all right. That is just the way that function is. Essentially, we are saying that if A is 0, then B is 0, then irrespective of the value of C, the result is 0. On the other hand, if A is 1 and B is 0, then depending on the value of C, the result is 0 or 1. That is just the informal specification, but let us just formally define it, that OBDD is a rooted directed graph. I did not put the directions here, but implicit in this figure is that we are moving from the top to the bottom. Okay. So, it is a directed graph, where a node V has an attribute of an index. Every node has an index. Okay. So, node A is associated with index 1. So, that index tells us the ordering of that variable. Yeah.
In terms of data structure implementation, so the leftmost path, which is A, B, and then we go to 0.
Yeah.
So 0 shouldn't be at index B, or we need to have an empty node there.
Indices are associated with variables. This is not an optimized representation yet. This is just the definition so far, but the indices are associated with only variables. Right. Here is how I define the OBDD. The leaf node has an attribute called a value. So, there is a value that is associated with these nodes, and for the leaf nodes the values are 0 or 1 that correspond to true or false. Each node V has two children, we call it low of V and high of V, and if a node V, its low and the high, these are like the children, the low and the high. If all of these are non-leaf nodes, then this holds. The index of V is less than the index of both its children. That is what is imposing the ordering in the OBDD. The graph is acyclic because of that. Once you do that, there is an OBDD that has a root node V. That index of V essentially represents some variable x, is one of the variables, right. So, that OBDD represents a function f in the following way. If V is a leaf with the value of 1, then that function is 1. Remember, the root is V. So, this is just a special case of a inductively defined function. If V is a leaf with a value 0, then the value is 0. These are the two base cases of the induction. But if V is not a leaf, then the value associated with V is, remember, the variable associated with V is x. Right. So, the value associated here is x prime times f of low of V. Low of V is the low child, and x times f of high of V, which is the high child. You can see there is an application of the Shannon's expansion. Right. So, essentially what you have at low would be the cofactor with respect to x prime, and what you have at high would be the cofactor associated with x. Just a quick example here for this graph with the variable ordering ABC, which means that first A equals 1, then B, then C. The function associated with each of these leaves is clear. The zeros means false, the ones means true. For this subtree, so for every node there is a Boolean function that we can associate. For this I have what? C bar or C prime times 0 plus C times 1. C is a variable, remember. So, that function would be what? Would be C itself. How do I represent C prime? So, this much is just C. What would C prime be? This function is C prime times 0 plus C times 1, that is C. How would I set up C prime?
Swap the 0.
Yeah, I just swapped the two leaves. So, just C is still there. There is no complementing on those variables, they are just variables, right. But I just have 1 0, then the associated function is C prime times 1 plus C times 0, that is C prime. Okay. So, that is my function for C. You can see that this subtree is identical to that subtree. Therefore, that function is the same function. What is the function for this? I have f equals b prime c plus b c, right. If it is true, then it is c. The result is c itself. What about the function for this? I have b prime times 0 plus b times c, that is b c. So, there is a function that I can associate with every one of the nodes once I come here. So, if this is b c and this is c, then I can go here and derive a as a prime times b c, that is this, plus a times c, which is this. Finally, the function that is corresponding to that entire structure is a c plus b c. Okay, let me stop here and we will continue in the next class.